Our lab today is about capacitors, and we're going to talk about how to, in particular, study the decay of the voltage across the capacitor when it's attached to a resistor. So we're really going to be talking about RC circuits. Now, for the longest time when I was very little, I thought that RC stood for remote control circuits, but it's not remote control, it's resistor capacitor circuits. So anytime that you have a resistor and a capacitor in series or parallel, that's considered to be an RC circuit. So this lab's going to have a pre-lab, and so it shouldn't be too much of a killer pre-lab, probably just a few minutes and you'll be good to go, but if you don't do it, then you won't be able to finish the lab in time. So we're going to talk a little bit about RC circuit theory. Here you can see a resistor and a capacitor in series, and there's a voltage that's across both the resistor and the capacitor. And so this V sub C, that's going to have an exponential voltage across it. So what happens is that when this switch here is closed, the voltage V sub S is going to appear across the capacitor, and that's going to charge the capacitor up to a particular voltage. Then when we open that switch, so we're going to temporarily close it by pushing a button, then we're going to release the button, and that's going to open the switch back up. Now this resistor and capacitor combination is isolated from the rest of the circuit. And so as a result, what we find is that the voltage that's across the capacitor is going to sort of flow around the resistor, and that means that it's going to decay. It's going to dissipate the energy as it goes through the resistor. And so slowly, the energy that's stored in the capacitor is going to be dissipated by the resistor until eventually it'll approach zero. It actually never gets all the way to zero, at least mathematically. It will exponentially decay towards zero. And so we're going to study this circuit in lab, right down to the push button switch to be able to charge the capacitor. So here's the equation that shows how the voltage across the capacitor as a function of time is the original voltage, V sub 0, so that would be whatever the voltage is at the top, the voltage supply, and then times e to the minus t divided by r times c. Now this r times c is a very important quantity. That's known as the time constant. So sometimes this equation will be written as V sub 0 e to the minus t over tau, because the Greek letter tau is used to represent the time constant. Either one of those equations is equivalent. So what you see is that if we knew r and c, and if we know a particular time, and we know the original voltage, then we can predict the voltage at any other time. So we can actually do that by looking at an exponential decay curve as well. Here you can see that we're looking at V sub C, the voltage across the capacitor, divided by V sub S, the supply voltage, sometimes called V sub 0. And at t equals 0, of course, we're at 100%. But as time decays, or as time passes, the voltage is going to decay exponentially. And the thing to know about exponential decay is that it decays more quickly at first and then more slowly as it progresses. Probably a good thing to memorize, or a good thing to have memorized, is that after one time constant, it will be at 36.8%. I just call it 37% of its original value. After two time constants, it'll be at 13.5% of its original value. After three time constants, it'll be at 5%. After four time constants, 1.8%. And after five time constants, 0.7%. Most people don't have those last few memorized. I would say talk to an electrical engineering senior. They probably know 37%. They might know 13%. But the 37% is the one that we probably all have as kind of a common knowledge. So we have after each time constant, it's kind of weird, by the way, that R times C is going to give units that are in seconds. So if you just take R in ohms and C in farads, then it'll give you time in seconds. But that's true, it does. So when you multiply those two numbers together, you actually get a time. And that time is how long it will take for the system to decay down to 37% of its original value. So given that equation, and let me just reemphasize again, this equation right here at the bottom of page 1 is the essential equation for studying this system. We're going to now do some pre-lab calculations, because I've pre-built for you 6 RC circuits. You can see here all of them have 56,000 ohms. So all of them have the same resistance, but the first one has 1,000 microfarads. That's a pretty high amount of capacitance. 470 microfarads, 100 microfarads, 47, 10, and 4.7 microfarads. So we have a range of a factor of about 200 in the capacitance. That's gonna cause basically a range of about 200 or 120 or so in the time that it's going to take for these circuits to decay. So there are a couple of ways that we could observe this. We could put it onto a multimeter, and we could observe the voltage decay by a multimeter. We could put it onto the oscilloscope. We could watch it decay on the oscilloscope, and you'll probably do that next year. But for this year, I wanted to do something a little bit more fun. So what I'm doing is I'm taking each of these circuits, and one at a time, you're going to attach it to an op amp. So we just learned about op amps, and this is one of the circuits that we learned about. This is the unity gain buffer. Sometimes it's called the voltage follower. Remember that the idea here is that whatever this voltage is on pin 3, it's guaranteed to be the same on pin 2. And then because we have a wire that's directly connecting pin 2 to pin 6, that means that it's the same voltage as pin 6. So pin 3 and pin 6 have the same voltage. But remember that the key here is that there's infinite input impedance on pin 3. That means that while pin 3 is observing what's happening to this circuit, it is not changing it in any way. So it's not taking extra current to drive this LED through the 220 ohm resistor over here. If we just attached an LED through a 220 ohm resistor, it would decay much more quickly. It turns out that, you know, if you take the longest of our decay times here is, you know, on the order of 1.5 minutes, it would take maybe 5 seconds for that one to decay if we didn't have this op amp in here. So the op amp is pre-built for you. All you need to do is connect this wire right here, and you'll connect the wire between the positive terminal of the capacitance and pin 3 of the op amp. You'll do that one at a time for each of these 6 circuits, and you'll see how long the LED stays lit. Now, I did an experiment for you that has saved you some time, and that is to see that the LED needs at least 1.6 volts to remain lit. So what that means is that the pin 6 must have 1.6 volts on it to go through the LED and to go through the resistor to ground. When pin 6 drops below 1.6 volts, then the LED will dim and it'll eventually go out. And so that means that since pin 6 needs to have 1.6 volts, that means that pin 3 has to have 1.6 volts, and that means that V sub C has to have 1.6 volts. So we can say, oh, you know what? We have an equation, this equation right here that tells us what is the voltage at any time given the initial voltage and then times e to the minus t over tau. So we know the initial voltage. In our system, we're going to set the power supplies up to be 9 volts. So the starting value is 9 volts. And then we have V sub C. We know that that needs to be 1.6. So the question is when? At what time will that occur? So you're going to need to calculate T divided by tau. Eventually, you'll just say that T equals some number times tau. You need to calculate T divided by tau. To do that, you're going to need to do a natural logarithm to get rid of the E here. So just be aware that this quick calculation here is going to require you to do a natural log. And then assuming that the value of R is the same for all 6 circuits, 56 kiloohms, we know that tau is R times C. So then what I want you to do is take the result from pre-lab question number 1 and figure out what is T as a function of C. And that's actually a much easier calculation than the first one was. So no logarithms needed there, just plain old multiplication and division. So we now know T as a function of C. We know that C is the only thing varying among those 6 circuits. And so you can plug in the values of C and calculate, first of all, you can calculate the time constant in tau for each one of those 6 circuits. And then you can calculate the time when you expect the LED to go out. So just as a rough ballpark, we're looking at between 1 and 2 minutes for the first one, and between 30 and 60 seconds for the second one, and so forth. So when you're in lab, you'll actually be doing those measurements and using a timer to actually observe the time that it takes for the LED to turn out. Then, of course, you want to measure it. So this is the decay time that you're going to be measuring when the LED goes out. And then I want you to calculate the difference, the percent difference from your prediction. So up here, these are the predictions that you made. And then I want you to calculate the percent difference of the actual measured decay time. My observations are that it was pretty good. It was not super far off. And so what I want to know is, what do you think? Given that the tolerance on the resistors is plus or minus 5%, do these results seem to reasonably confirm the equation that we used to derive the predictions that we made? And then, do you see any sort of systemic error? In other words, are the LEDs always on longer than you had calculated, or do they always turn off earlier than you have calculated? If so, what do you think is causing that systemic error? Can you think of any possible causes why it would be a little bit different than what we had expected? Then the last thing is designing the RC circuit. So there is a seventh sort of position on the board, which has another 470 microfarad capacitor, but no resistance. And so what I want you to do is calculate how much resistance would you need to have a 10-second LED time. So you push the button, the LED stays on for 10 seconds, and then it goes off. Now you can do this as a pre-lab question if you want to, or there'll probably be time for you to do it during the lab if you'd prefer to do that. And then tell me what value of resistance that is. Plug that value of resistance in and see if you get 10 seconds. You should get pretty close. It should be, I think that when I did it, I got about 10.7, 10.8 seconds. If you find that you're lower than 9 seconds or more than 11 seconds, adjust the value of the resistance. It probably just means that either maybe the capacitance is a little bit higher or lower than what we had expected. So that means that the resistor needs to be a little bit lower or higher than we had expected. As soon as you get to the place where your circuit lights for 10 plus or minus 1 seconds, then just demonstrate it to us and you'll be done with lab.